Welcome everybody. Thank you for joining our session today on transforming energy agents for energy. My name is Brett Alba. I'm joined here today by Nitin Chaudhary. Today we're going to be taking a deeper dive at enhancing petroleum engineering workloads with Databricks agents. We'll begin by setting the stage with some current challenges in petroleum engineering analytics and workflows. Then we'll dive into how democratizing analytics with Databricks agents is really changing the game for several of our customers. Once we get through the slides, we'll transition to a live demo showcasing some of these AI-powered petroleum analyses. And finally, we'll conclude with a live Q&A. So please either hold questions till the end or feel free to drop them in the chat. We have Jason online, as well as myself and Nitin that can answer those questions throughout the presentation. Real quick, just to start off with a brief forward-looking statement, the information we present today is for informational purposes. As of the time of this recording, some of the products that we'll be discussing are still in beta, so definitely see them maybe changing before we make it to GA, but all for the better. Awesome. Well, before we get started, I want to take a moment to introduce the team here on the call. As I mentioned earlier, my name is Brett Albo. I bring 7 years of oil and gas industry experience to Databricks with sort of focuses in data science and data engineering. I've worked at several upstream companies, including EOG Resources and Apache, where I got some firsthand knowledge to some of the challenges that we'll be discussing today. My most recent stop was at Meta, where I was a data scientist and data engineer. I joined Databricks back in December of 2024, so almost a year now, and I'm based in Boerne, Texas. Nitin?
Yeah, hello everyone. Nitin Chaudhary. I'm a senior solutions architect here at Databricks. Before joining Databricks back in July 22, I was a petroleum engineer for almost 12 plus years. My background is I did a lot of research and applications of ML and AI in solving petroleum engineering problems. And super excited to meet everyone today and looking forward to a lively discussion.
Cool. Awesome. So let's start off with discussing this discussion by looking at some of the challenges that are often faced within petroleum engineering analytics. We're going to sort of take a look at our expert, Tim, who is a typical petroleum engineer. He's often facing difficult time-sensitive decisions with huge data sets. For instance, in this scenario, Tim needs to analyze 200 wells, understand decline curves, and recommend actions all before tomorrow morning's production meeting. Tim's main challenge is his analysis is multifaceted. He must correlate complex well completions, decode downturns in production, and suggest interventions, often with incomplete data and limited time. These are problems that engineers regularly face throughout our industry. So the first stop for Tim, like many in his shoes, is to answer some of these questions using business intelligence dashboards that his company's IT or analyst teams have stood up. These dashboards are really good for KPIs and maybe finding overall trends, but they don't necessarily answer the deeper technical questions like decline by completion type or what if scenarios for reservoir properties. It just, it's impossible for a dashboard to really have every single question that Tim might have answered. So in short, these dashboards can tell engineers like Tim what happened, but they rarely say why it happened or how he should react. And so for the next steps, after he's moved on from his BI dashboard, to get a custom analysis or to get that dashboard modified, Tim has to submit a request to a data science team or business intelligence team, which at a minimum, this can take 2 to 3 weeks with multiple back and forth and clarifications from the analyst that might not know petroleum terminology or understand the physics-based stipulations around the data. The result is really long wait times and frequent miscommunication. So the report may not even answer the original question Tim was after. For larger requests, that might require additional data sets to be created. We could be actually looking more like several months as opposed to several weeks. And so finally, with all of his options exhausted, Tim tries to go down the DIY route and solve this problem himself, trying to write his own SQL. Unless he's an expert in both petroleum engineering and advanced coding, he quickly runs into problems with complex joins, sketchy data, debugging, syntax errors, and potentially resulting in unreliable results. Tim's time is best spent solving petroleum problems, not wrangling SQLs. That's what we want to enable him to do. In this code snippet above, we see Tim was having trouble with some joins, as well as some missing null checks. And so, these are all nuanced problems that analytics professionals are aware of, but petroleum engineers just aren't necessarily trained in that. And so, these nuanced problems can really stack up, leading to Tim to still not having the answers he needs for the call in the morning. This scenario Tim faces is very common, from miscommunication and long turnaround times to engineers losing valuable hours on data formatting, rather than focusing on high impact analysis. In fact, we've seen studies that suggest that 63% of executives cite inflexible analytics as a huge pain point, and 70% of engineering hours are wasted on data wrangling, not actual value generation. So this is where we feel like Databricks has a place to step in. Databricks is transforming energy analytics, breaking the bottleneck, returning valuable time to experts, and providing immediate actionable insights through powerful agentic tools. As we sort of set the stage for Databricks agents, let's clarify some definitions of what agents are. In technical terms, an agent is a compound AI system capable of reasoning through complex problems and calling on various other tools to assist. You can think of agents as digital coworkers. They hold context, converse iteratively, and can orchestrate specialized helpers or tools as needed. And this isn't just a chat bot like many of us are used to leveraging. These agents sustain multi-turn conversations, pick the right tool for the job, iterate on outputs to solve nuanced domain-specific challenges, such as Tim's that we previously discussed. Databricks has really been a thought leader in this subject. This paper, which Nitin just shared in the chat, was written by many of our co-founders back in early 2024 discussing this concept. The power is not necessarily in the specific large language models that we see being iterated on continuously, but in the compound AI systems themselves, which we'll continue to define. With that continuation of definitions, let's start with a conversational agent, which is an advanced form of AI designed to engage users in natural multi-turn dialogue, stimulating human-like conversation. Unlike simple chatbots, conversational agents do much more than provide scripted or rule-based responses. They use technologies like natural language processing and machine learning to truly understand the context and interpret user intent and respond dynamically. These agents maintain a history of the conversation, which really makes them special. The real power of conversational agent lies in their ability to adapt through the interaction, making each answer more precise and relevant as the dialogue progresses. In the context of analytics, a conversational agent empowers domain experts like our petroleum engineer, Tim, to ask iterative technical questions using everyday language and receive immediate contextual insights. This unlocked new efficiencies and depth in problem solving, replacing slow, fragmented processes with intelligent, human-like assistant that's always available. No more long BI queues to wait around. In the context of analytics, next we have tools, which in the context of analytics, a tool is a distinct function or software component created to perform a specific task in one step. Think of a tool as a digital instrument. It might pull data, perform calculations, generate a visualization, or apply some particular algorithm. What's important is that tools are not generalists. They're usually highly specialized and designed for efficiency, reliability, and repeatability. When an agent needs to solve a problem, it calls on different tools as needed to accomplish these analytics or operational steps. In our petroleum scenario, tools could include functions for decline curve analysis, well data aggregation, or generating statistical reports, all working behind the scenes at the agent's command. This enables complex solutions to be constructed flexibly and on demand by combining the right tools in the right sequence determined by the agent itself. For domain experts, this means they can focus on the what and the why, while tools effectively handle the more technical how. A tool calling agent, while similar to the conversational agent previously mentioned, is an advanced artificial intelligence system that dynamically invokes tools we previously discussed to complete tasks. Unlike traditional chatbots or assistants that only generate text, tool calling agents recognize when an action must be taken, identify the most relevant tool based on the context, and execute it with the needed parameters. The agent's workflow starts with understanding the user's intent, reasoning about which tool to call, then orchestrating these tools in sequence or combination until the user's question is resolved. For example, in petroleum analytics, a tool calling agent might fetch production data, apply an analysis, and even generate custom visualizations, all without intervention. This ability transforms agents from passive information providers, like the conversational agents we previously talked about, into active problem solvers, really bridging the divide between domain expertise and technical capability. Tool calling agents thus empower experts to focus on decision making while leaving the technical execution and data manipulation to the AI-driven automation. And then finally, to sort of wrap up our definitions before we jump into the demo, we have multi-agent systems, which in more advanced scenarios, agents can coordinate among themselves under a supervisor agent, sharing information, delegating tasks, and converging on the optimal answer. This multi-agent approach is like really assembling a team of experts, each focused on a specific analytical process, yet seamlessly sort of integrating to tackle a full workflow. That's how Tim's needs are met quickly and comprehensively, with each agent amplifying its own domain expertise rather than replacing it. And so, finally bring this back to the actual implementation. Our Agents4Energy initiative really leverages several specialized AI agents within Databricks, each tailored for the needs of petroleum engineering. These agents bridge the gap between domain knowledge and data science, making sophisticated analysis accessible to engineers from day one. Nitin will be going over each of these agents in detail, but as a preview, I just want to highlight some of these that you'll hear in the upcoming section. First, we have our data science agent, which offers fully autonomous multi-step analysis from engineers' questions to actionable insights. And so being able to easily develop plans and solve problems continuously. Our AI BI Genie, which is used for conversational natural language queries and instant answers on tabular data. And then finally, Databricks, which is some of our newest agentic offerings, which really brings production-ready agentic systems to your most valuable problems right out of the gate. And so with all this done, when the agentic solutions are stood up, we'll see a very dramatic impact. Databricks agents transform analytics from a multi-day, multi-step process to one where answers and insights flow in minutes. Tim and domain experts across the field gain direct control, reliable methodology, and scalable workflows that put their petroleum expertise front and center. Instead of bottlenecks and busy work, agents deliver immediate, reproducible insights, empowering experts to optimize production faster and smarter. Tim's workflow now goes from days waiting for DS support, multiple handoffs, uncertain results, to an agent-powered workflow that provides analysis in minutes, reliable and reproducible methodology, and is scalable across multiple business units. And so we'll now transition. I'll stop sharing and pass over to Nitin, where he's going to actually put some of these insights we've recently gleaned into practice.
Thanks, Brett. Give me 1 second to pull up my slide deck here. Okay, perfect. Brett, do you see my screen? Okay, awesome. Thank you.
Yes, yes.
So thanks for setting that up, Brett. So today for the demo, what we are going to do is we're going to build a demo scenario, and I'm going to sort of go through a very, very rudimentary view of the multi-agent architecture that we are going to build. And then we're going to go into the actual demo. So think about an upstream company, Helios Petronorth, right? The scenario is made up, but it's very close to the reality that I have faced multiple times in my previous role as a petroleum engineer or a production engineer. So Helios Petronorth is an independent upstream operator focused on unconventional oil and gas production across the Permian Basin, both across Midland and Delaware subbasins and Eagle Ford as well. The assets are managed by area, meaning there's an asset for Northern Delaware, Central Midland, Eagle Ford, with production that's delivered into multiple midstream pipelines via pad level gathering and central compression. Now, on August 22nd, 2025, recompletion on one of the Bison pads in Northern Delaware led to sand screen failures, which then eventually led to compressor trips, rising water cut, reducing the wellhead pressure, ultimately reducing the production and leading to lost revenue of almost $5 million per day. This is a massive event that everyone wants to be on top of. So the first thing that the chief production engineer wants to do end-to-end monitoring to trace and deep dive into the incident. Everyone wants answers as to what happened, why it happened, how can we resolve it, and what can we do in the future to prevent this from happening again. So now the production engineer comes in who starts to do a root cause analysis, but the current state that the engineer has to deal with, right? They might have to go look at production forecasting report, which is tool X. They might have to go look at equipment state, which is tool Y. And then they might have to pull up operating manuals for that equipment, which is scattered across multiple PDF files. So there's already an incredible amount of cognitive load on the engineer to perform this root cause analysis, which with the current state takes him or her or them days to weeks to gather all the necessary data from and sort of do the analysis across this tool sprawl of multiple tools providing access to multiple different types of data, which then again delays not only the mitigation of the current event, but also doesn't build a full picture for the engineer to be able to do future mitigation. So current state, it could take days to weeks to not only mitigate the current event, but also apply the learnings to future events so that the mitigation can be faster, which again, eventually could lead to millions of dollars in lost revenue. And this is a very common scenario that we have seen across multiple upstream companies of any size, be it an independent operator to a integrated large scale operator. And the tool sprawl and the problem is usually the same, regardless of the size of the company or the number of wells you might be operating. It's just that the more the number of wells, the higher the cognitive load and the more complex tool set that the engineer has to parse through. So how do we solve this? To solve this, we are going to build, as Greg mentioned, as Brett mentioned, that we are going to build a multi-agent supervisor. And this is kind of that architecture of that multi-agent supervisor. So there's a supervisor agent that routes between different agents. There's an agent that can pull the well data. There's an agent that can pull the equipment state and the equipment data for all the compressors across the pads, as well as the pipeline being monitored. And then there's an agent number 3, which can do Q&A on the equipment operating guidelines, right? And then you can imagine multiple other agents that could be relevant to pull information for a scenario like this. What this does assume is that you have already invested in a lakehouse architecture on Databricks, where you have been able to ingest data from multiple sources. We'll briefly touch that during the demo, but that's kind of not the scope today. The scope here is that you've already reached a state where you have standardized some of this data under the hood, and now we are sort of building a experience for the engineer to be able to do that root cause analysis much faster than what they've been able to do in the past. So with that, let's switch to the demo. I'm going to stop sharing my screen for just a second here. Okay, very good. Can everyone see my screen now? Yep, thanks, Bud. And also, as I'm going through the demo, and as you guys see something sort of on the screen or in the scenario that I have set up, if you have a question, or even if not a question, if you have a comment, please, please, please post on the chat. Let's make this interactive so that we can all learn together better. Okay, so let's get started. So I'm going to start with the end state here, right? So I am a production engineer, and I was just recently told that there is a tool that can help me do root cause analysis. And I get a link to a tool. I open my browser and I land on this page. Now, what this is the front-end interface that's under the hood calling different agents to pull different information. But the production engineer doesn't need to care about all that, right? For the production engineer, we're sort of in this front-end phase, and the production engineer can sort of start by asking simpler questions, right? First, I want to just understand what this thing can do, what kind of data it has access to, those kinds of things. So as you can see here, I'm already getting some sample questions here that are being suggested to me, but I'm going to start with even more basic questions, right? I'm going to say, how many wells do we operate in northern Delaware? Because I am responsible for the northern Delaware basin, so I only care about northern Delaware wells, right? So it's going to start and it's going to sort of bring, it's under the hood, this question is firing the agent that can answer my question and sort of generating the answer for me. And here's the answer. We operate 552 wells in the northern Delaware. So the next obvious question here, as you can see, it's already sort of suggesting to me, right, what I might be interested in next. And this is what I usually would be interested. What is the production performance of wells in northern Delaware basin? And again, it's going to sort of now call that production agent that's going to be able to pull up the information about the wells. And I can already see that here's some, it gave me a list of all the wells, all the 552 wells, and it also gave me a list of top performing wells, which would anyways be my second question, right? So there's an Antelope well, there's a Buffalo 322 well, there's a Buffalo 408 well, so and so, and it kind of gave me a list of top 10 wells, and I also have access to information for all the wells, 552 wells in northern Delaware, right? So again, this is where you can start seeing the difference of having access to a multi-agent supervisor here for the production engineer versus a dashboard. Whereas you could put this table on a dashboard, right? But what the dashboard can't do is do follow-ups, right? Because anyone who looks at a dashboard almost always has follow-up questions looking at a chart, right? And especially remember, we are still in that root cause analysis mode. So I might not see some information that I need to be able to drive that root cause analysis. So what do? I then go to the analyst who maintains the dashboard, who would then sort of add more charts, and the timeline that Brett showed us, that could take weeks for the dashboard to get updated. And I don't have that kind of time for my root cause analysis. Maybe in the future, adding those things to the dashboard would be helpful. But then you also run into a scenario where it's death by 1,000 dashboards, where the dashboard has thousands of charts now, or you have sprawl of 1,000 dashboards, which again is no different from having to go to different tools to get that information in the first place. So what if we could sort of talk to the dashboard? And that's where this kind of paradigm comes into the picture. And as we go later, we'll talk about how you can integrate this to sort of your existing internal dashboards and things like that. All of this experience can be built with API endpoints and integrated into your internal tools, right? So now, my next question would be production variance, right? Because that's kind of where the root cause analysis event would have led to, right? Because we had a lost production event where we lost revenue. So let's understand the total production variance for wells in northern Delaware. So that's my next question. What is the total production variance for wells in northern Delaware? And it's going to give me an answer for a total, right? And I can then ask it to say, show this spread across wells with highest variance in August, right? Remember, our event occurred in August. So my next question here would be natural. Show me the spread across wells with highest variance in August. Again, this is doing its magic behind the scenes, firing off multiple agents that can bring that information to me, right? And looks like it was able to figure out that there were some wells that had the highest production variance in August, Mustang 6, Mustang 7, and these variances are quite high, right? So now I'm going to sort of switch gears and I'm going to say, okay, now I'm starting to care more about let's switch gears here and then start to ask questions around equipment failure, right? So yes, the production makes sense, but I also want to understand this variance at a compressor level or at a pad level so that we can understand how that production variance has changed, right? So let's talk about compressor failure modes, right? Let's see how many failures did we have in August. And this is gonna, again, give me an answer. And I clearly have made a spelling mistake, which is very typical of me as a petroleum engineer. Anyway, so it's gonna sort of give me an answer. Okay, you had 48 failures in Northern Delaware. Remember, I didn't give it that in this question, you will notice I haven't said or mentioned Northern Delaware at all, right? It remembers the context from the previous conversations and is able to understand and figure out that I'm still talking to it about Northern Delaware Basin because it can remember the context that I started the conversation with because it has conversational history built into it. So that's great. 48 failures occurred. So let's dig into what type of failures occurred in August. And now this is going to sort of, again, remember, it has access to production data. It has access to equipment failure data as well. And there it is. This is that biggest event that occurred. And most of the failures were because of sand screen control, right? It looks like all of these have similar code for sand screen failure mode, right? So now let's talk about interventions, right? What types of interventions occurred in August? Because I want to understand the failure and what intervention occurred due to that failure. So now I'm going to talk about interventions occurred in August. And you can see here that this was that recompletion operation type that led to the sand control event, right? So the intervention chain makes so much sense here now because the sand screen failed on the recompletion event. And because of that, there was a sand control issue and sand started to flow into the well. And because of that, the compressor was, the pressure dropped and the compressor was about to fail. So we had to do a choke change, which led to the production variance. So now let's do something much more complex. These were very point questions, right? But this is not really helping me get to a very detailed root cause analysis, and I don't want to keep asking it question. So now I can switch to something that we call a research agent, right? And I'm going to have to switch to a new chat. That's fine. And in the research agent, I'm going to ask the question of what can we do to improve equipment uptime, right? And this is gonna help me understand and do a deep dive into what might have gone wrong. And again, so the point is to understand the event that has happened, to understand what mitigation took place, and to understand what can be done in short, medium, and long term to prevent these types of events and do a better mitigation in the future so that there is less production lost for an event like this. This is exactly what my chief production officer has asked me to provide as an information. And this is the kind of thing that would take me days or if not weeks to go through multiple tools and pull all of the information together. Or I could switch to research agent, which is a deeper dive, right? It's going to call even more agents under the hood and do a deeper thinking on what has happened and how it can be improved with all the access to all the data that it has under the hood. So let's switch to that. And as you can see, because this is a deep research mode, right? First, it's going to build a plan of actions, right? So it's going to, because my question is very vague, because again, right, I'm operating in a low information scenario here. I was just woken up at 3 a.m. and told that there was an event and we need to do a root cause analysis and sort of tell to the leadership what has happened and how we can ensure that this doesn't happen so that we don't end up losing millions of dollars in revenue. So now what it's doing is it's sort of thinking through the question. It's breaking my question down and creating more deeper questions to then go ask other agents under the hood and sort of trying to recuperate all that information so that it can do the analysis for me. So if you want to follow along the thoughts here, right, it's sort of saying what is the current equipment uptime performance? This question will establish the baseline uptime performance. Next, it's looking at equipment uptime trends over time. So again, it's now has identified that CS17 was the key underperforming compressor, which had only 80% uptime in 20 trips. And it has established a baseline performance across all equipment, compared CS17 to that to understand what has happened within the August-September timeframe. It has identified Bison pad as having the production issues. And by examining the weekly trends, it can identify when the uptime deteriorated and whether there are patterns that suggest specific intervention that lead to these types of events. And it will do a temporal analysis for understanding previous events that might have led to this event. And then it will move on to root causes for the equipment downtime. So as you can see, right, it broke down my question into three deeper questions. First, it needs to understand and figure out what is the current equipment uptime performance. Then it needs to understand equipment uptime trends over time, and then do a root cause analysis for the equipment downtime. So it's currently in that second phase of executing the research on uptime trends over time. We'll let this think for a minute or so. And let me just check the chat here if there's any questions. Okay, Brett, I think people have been putting questions in the Q&A section as well.
I'm answering them. We can, getting several questions on trusting the results. And so I've been answering a little in the chat, but sort of about around the benchmarks and monitoring tab that Jeannie has to offer. Maybe we can save that for the end though.
Okay, very good. And while this thinking is completing, the one question I do want to pick up is from Henry. Is the research agent also part of the Genie, or we need to build it? No, it is part of the Genie. Everything I am showing here, right, once we sort of go through this demo, and I'm going to switch to show you what the underlying agents look like. All of that is no code. I didn't write a single line of code to build this interface, to build the deep research mode, or to build the underlying agents that this interface has access to. Everything was low code, no code, right? And the only thing is that my data engineers have done a fantastic job of curating this data, right? And created a set of tables that I can use to build it on top of those. But beyond that, there was no other code written to do this. And others just had a question on, does all the data need to be in Delta Lake Unity catalog? Can it be connected to external resources as well? That's a really good question, others. So the answer is, it doesn't need to be in UC, right? We have this thing called Lakehouse Federation, where you can build agents on top of any type of a source data system, be it Snowflake, be it any AWS tooling, any Microsoft tooling, Oracle databases, Microsoft SQL Server. You can build that connection with UC that will federate the queries down to the source systems, and then Genie can still orchestrate, and the agents can still orchestrate queries and pull the data from those external systems as well. And then Frank had a question on what LLM model the research agent is using. Yeah, that's a very good question, Frank. We use a multitude of underlying LLM vendors, right? Be it OpenAI or be it Anthropic. The key distinction here again is the fact that Brad referred to earlier in his presentation with compound AI system, right? Where the underlying LLM model is completely abstracted away from the end user. You shouldn't have to follow all the new research and the new models that keep coming out every 2 months, every 3 months, and sort of get bogged down with all the benefits and limitations of underlying or individual LLM models. We take that problem away from your hands. Let us and our R&D team figure out which is the best LLM model for the agent that you are trying to build and orchestrate on top of. And you still get the best experience and the best accuracy for the end answers. Okay, very good. So I also asked this question, and you can see how it's sort of thinking and building the previous thoughts. I had asked this question earlier in the day as well. So I'll just switch to the answer that was already generated for this, right? And once it would have finished, this is what it would have looked like. So if you notice here, this is the plan that it created earlier. Where it first, again, right, current equipment uptime performance, it found the CS17 compressor, understood the root causes, and then tries to build a correlation between interventions and equipment trips, understands the post-completion failure timeline on Bison pads, fleet-wide compressor failure root causes, and then identifies that, oh, there were specific valves which had sand screen failures, which is what led to the compressor being under the downtime. And if I sort of show the thoughts here, you can see the model, see the agent systems thinking and talking to each other, right? If you sort of read through all of this, right, it took my question of what can we do to improve equipment uptime to like more initial validation questions. Then it fired up deeper research into current equipment uptime performance, all the things that we saw in the plan, and how it was thinking back and forth with different agents. And ultimately, it produced this analysis for me. So let's go through this, right? Because this is what we've been sort of building towards. So it first identifies that the equipment uptime across North Delaware's compressor fleet dropped to 45 to 65% during the August to October 25 timeframe. This is that event, driven by a catastrophic sand screen failure affecting all 48 wells on the Bison 3 and Bison 5 pads. Why did that fail? Because there was a sand egress that caused 56% of the CS17 compressors downtime and downstream affected 25 plus compressors across the entire fleet of compressors that we maintain for the Northern Delaware operation. Why did this happen? Because there was 100% failure rate of this new mesh sand that we have started to use, which is HX120 mesh. And the screens were sort of failing. The sand screens, the HX120 mesh 120 sand screens were failing within 72 hours of the August 22 recompletion. So this in itself is a fantastic summary of what happened and how it happened, right? It was able to identify from the data live that this was the impact and underlying cause of the event, right? And if you notice here, I remember there was a question about trust, right? Which is super important here. Again, this is something that you wouldn't be able to do with just a direct OpenAI chat because it doesn't have access to all the data that your amazing data engineers have curated for you. So here it's giving me the source information of how I was able to pull out. So if I click on this, it will give me a research summary of how it led to this answer, which I can then go in and read further in detail and understand and look at the data and how I was able to figure out that between August 24 to August 26. Remember, the event occurred on August 25, how there was a change in the SAN screen failure rates between Bison 3 and Bison 5. And there's even a note being captured from the field engineer that, hey, there was a post-completion reinspection and evidence suggested that there was a SAN screen breach, and this specific alarm had gone on the compressor side, and hence this failure code was generated. So you can see that this is how we build trust into the system. Again, you don't have to do anything to sort of build these citations. It automatically pull those out and give you a summary of what happened. And then once you click on the citation, it will give you the data that backs up the conclusion that it is showing you. And then if you go deeper into what was the root cause, it tells you that there was a SAN screen design failure, that how the recompletion on Bison 3 and Bison 5 pads had installed a HX120 mesh screen across all the 48 Bison pad wells. And within 24 to 18 hours, every single well experienced the SAN screen breach, which triggered the SAN ALM alarm, forcing an emergency choke restriction from which reduced the choke opening, right? Where we had to apply a 40% choke restriction. Again, I can sort of click on this to go deeper into the analysis of how that event unloaded, right? You can see here between different dates, you can see that on August 25, there's all these choke change events that have happened on specific wells within the 3 and the 5 Bison pads. Again, building trust in my observation. It shows that data summary here as well, right? And showing that how the choke was restricted severely by 40%, which then what that would have probably meant is that the compressor upstream to the those specific pads wasn't aligned with that much pressure reduction, and hence the failure event happened. The universal failure pattern here is that there was a fundamental design inadequacy or incorrect screen specification for the reservoir conditions for those specific wells in Northern Delaware Basin. It doesn't look like this was an installation quality issue. Again, super important for that root cause analysis, right? Because if you want to do future mitigation, because we are also planning a recompletion for the Bison 5 pad or some other pad, Bison 6 pad that's neighboring. So we want to make sure that this wasn't an installation quality issue. So we don't need to go change the supplier of the SAN screen. Instead, we need to go talk to the reservoir engineer to understand what correct SAN design should we use, right? What SAN size should we use? What mesh size should we use for the SAN equipment? And similarly, then it goes deeper into okay, what specific compressor failed here? It shows that CS17 experienced 24 hours of downtime, and the fleet-wide analysis reveals SAN-related failures dominated that downtime, and then there was CCCS07 that logged 20 hours of SAN ingress downtime. Okay, first step is complete, right? I can send this summary confidently to my executives to help them understand what has happened. And we have also understood, because in 2 weeks' time, we were going to start the recompletion on Bison 6 pad. We have also understood that this is not an installation quality issue. We don't need to go change the supplier because the SAN quality itself is fine. It was a design issue. So we need to go talk to the reservoir engineer to understand what would be a better mesh size for this specific rock formation. right? And then if I scroll down here, it also gives me some other summaries around what should be our recommended action, right? So it clearly shows that there was a rapid degradation on both. Water cut climbed, wellheaded pressure dropped, and compressor event spiked from 314 per day to 15 to 25 post-event, right? Emergency choke restrictions remained in place throughout the September, which means there was lost revenue throughout the September because of reduced choke size and reduced production, right? And then it also gives me some recommended actions, right? So maybe we should do a metallurgical analysis of the screens to determine the breach mechanism. And we should also talk to our reservoir engineer and understand what particle size distribution should we use to understand, is this the right screen mesh size that we should be using? Maybe we should evaluate alternative sand screen technologies. Now, you might be thinking, how does it know all of this? How does it have all this contextual knowledge about sand screens and completion technologies and reservoir modeling? It's because we have that other agent that has access to the operating manual that our SMEs have generated internally that tell us what is our internal design process to pick a sand mesh size? What is our internal design process to pick a vendor to supply that sand mesh size? So because it has access to all that unstructured data under the hood, it's able to generate these recommended actions by summarizing our operating procedures that currently exist. And then if you go through here, there are long-term analysis that lead to helping us understand what is happening. So current approach, reactive choke management and repeated compressor repairs cannot restore our uptime, right? Long term, we need to replace our failed sand control system with a design validated with the reservoir engineering team for the Northern Delaware's reservoir condition. Now, this is something I can take to my executives and help them understand that, hey, this is both a design and a process issue, and these are the things we need to do to make this work better in 2 weeks when we are about to go do a new recompletion and build that confidence that we have the ability to recover from this. Okay. So I'm going to switch back here to close out, right? I'm just going to give you a sneak peek of how I built this, right? So first of all, if I switch and if you go in Databricks, right, there is a new agents button here that I can click on. And specifically, I built those 3 agents that we were talking about, right? So there is this forecast traceability assistant and then the production risk assistant. So if I look at this production risk assessment, what it's doing is I've configured a knowledge source. What that does is it points to a volume of PDF files. And if I just open that here, which contain our standard operating procedures of how to operate choke, what type of recompletion strategies have we used, past events impact analysis that somebody curated painstakingly. It has some playbook overview. It has market data dashboard screenshots. So a lot of that unstructured data is built into this knowledge assistant is what we call it, right? And I can individually interact with just this knowledge assistant as an agent as well. And I just see a question from Frank. Yes, this is multimodal. It's not just textual RAG, meaning you can have pictures in this as well, and it will be able to extract information from those pictures and be able to build the knowledge source for you. And then I also built a multi-agent supervisor, right, that combines, oops, sorry, let me go back here. That combined the knowledge assistant for the unstructured data and a Genie assistant that we were looking at earlier on the structured data like equipment data, production forecast, production time series data, any type of SCADA stream that you might have monitoring the compressor state and the alarm state. All of that structured data is sort of built on using Genie, and then Knowledge Assistant is for the unstructured data. And we were able to bring those together, build this multi-agent supervisor. And this is what we were looking at earlier. And this is how he was able to, under the hood, route to different agents with different questions and curate that information for us to give us an analysis of what has happened, how it happened, and what we can do to mitigate in the future. Okay, so now switching back to our presentation, right? Let's do a quick recap. Remember, we had a sand screen failure causing compressor trips, rising water cut, wellhead pressure decline, lost revenue. We wanted to do a root cause analysis of what has happened, how it happened, how can we change that and improve that in the future. That was our current state, which would have taken days or weeks to gather all of this necessary data, right? So we would have never been able to do this before the next 2-week timeline for finishing or recompleting the Bison 6 pad. And the new state is production engineer was able to do this root cause analysis in under an hour. That end-to-end tracing leads to faster recovery, right? Saving millions of dollars in lost revenue, and was also able to help us build a better mitigation strategy for future scenarios to avoid this from happening again for the Bison 6 pad that we are about to recomplete. All of that analysis done in less than an hour, whereas today the production engineer, it would have taken days or weeks to do that with an increased cognitive load. And what happens if there were multiple events happening in parallel? You can imagine this is where the sky starts to fall apart. But with the new state, the engineer is much more productive to be able to do, handle these simultaneously, right? It would be as easy as starting a new chat with that interface and letting it offload multiple incidents and letting it work in parallel as you sort of try to build a narrative and a story and do more productive work, which is your real job, right? So that brings us to the end of the demo.